Today is September 21st, 2022. It is Wednesday. It is also day 4:30 of data science, and today I'm going to find the area above a point. So I'm going to do it with Python first because it's faster, and then I'll do it with the TI-83, the TI-84, and then using the z-score method, which is what College Board likes. So I'll start with Python. So the idea is that we have a set of middle school students whose heights are normally distributed with a mean of 150, standard deviation of 20. Uma is a middle school student with a height of 165 centimeters. So we're looking for the proportion of student heights that are higher than Uma's height, basically, like what percent of student heights, like of students are, or the students' heights are higher than Uma's. So first of all, we would need like the normal function. So I would just go from scipy dot stats import norm. So that's kind of this equivalent of normal CDF in your calculator. And then I would just do norm dot SF. So instead of CDF, we're doing SF because it's asking for a proportion higher than. And in Python, it's a bit different because in Python, CDF only finds the proportion or the area below a point. So really, we are looking for 1 minus CDF, which is the equivalent of SF. SF is literally just 1 minus CDF. So you would just use it if you're finding the area above a point, and then you would use CDF if you're finding the area below a point. But we're looking for the proportion of students' heights that are above Uma's heights or higher than Uma's height. So this function takes in three parameters: the point x, the loc, which is the mean, and the scale, which is the standard deviation. So x again is just 165 because that is the point of interest that we're trying to find the area above of. And then I'm just going to set the mean, which is 150, and standard deviation, which is 20. And then I'm just going to run that, and then I'm just going to round that answer. I'm going to set it equal to prop for proportion, and then I'll round a prop to 4 decimal places because that is what Khan Academy is asking of us. And then hopefully that runs anytime soon. All right, so I'm going to copy that and paste that in here, check if I'm right, and I am. Okay, so basically that is the proportion of students' heights that are higher than Uma's height. If we really want to look in percentages, it's 22.66% of students' heights, or at least we could say 22.66% of students. Would that be fine? Saying students are taller than Uma. Yeah. So that was with Python, and then I'm just going to do it now with the TI-83, TI-84, and then the z-score method, which is again what College Board would want. So let me get my pen out. So essentially the TI-83, why is it so thick? Okay, let me erase that. So to get to the normal CDF function, you need to go to second, which is like the yellow button on your TI-83. Then you would go to vars, and then you would click on 2, and 2 is your normal CDF, basically. I'm not going to write it, but yeah, it's a normal CDF. And when you click on 2, it's just going to appear like this. So this is what you're going to get on your screen. That's all they give you, and then you should know basically the points that you have to put in. So with the calculator, it's a little bit different from Python. So Python just has CDF find the area or proportion below a certain point, while the calculator takes in an interval and then just finds the area within that interval. And so for us, that interval it would be like our starting point. So our lower bound, our upper bound, and then our mu and our standard deviation. So our lower bound and upper bound is basically our interval for which we're trying to find the area of. In this case, our lower bound is what we start with, and that is a height of 165. So that's going to be 165. Our upper bound is actually infinity because remember, a normal distribution is a continuous curve that is never ending, right? So it means it goes on to infinity, and that is the proportion we're trying to find, the proportion just above 165. And so really what we're trying to have here is infinity, but unfortunately our calculators don't, or they don't have like an infinity button. So instead, we use a big arbitrary number like 1e99, which we can get by pressing, let's see, 1 on your calculator, then you do second, And then you do comma, which is kind of like where the J is above the 7. So you do 1 second and then comma and then 99, and that represents kind of infinity, right? Um, so then the mu you would put in 150, and the standard deviation you would put in 20. Enter now, just press enter, and then you should get the answer. And then really, you would just have to round yourself, and you would just have to know how to round because I don't think is there a round function in the calculator? I don't even know, but yeah. So you would get this 0.2266272794, and you would just have to round um like this and just know that that would be your answer that you would put in Khan Academy. So that's what the TI-83, pretty simple. Let's move on to the TI-84. So TI-84 is literally the exact same thing. The only difference is the format for which you input it. And it's actually easier, honestly, because it tells you what to put in. So it's the same way to get there. So second, vars, 2, which is normal CDF. And then once you get there, instead of just normal CDF in a parenthesis and then nothing, it actually literally lists the things that you have to input. So it says lower, upper, and then it says mu, whoops, that's sigma, mu, and then sigma. So again, mu is mean, sigma is standard deviation. Those are the symbols, by the way. And then it has this little like paste thing that when you hover over it, it turns black. So it literally tells you what to paste in there, which is so much easier. So then you would really know, okay, the lower is a lower bound, right? So again, is the same thing, 165. The upper bound is where we're ending, like when we're trying to stop finding the interval, which is really never, which is infinity. So we don't have infinity. 1 E99 is what we put. Then mu is 150. That's the mean. Standard deviation, which is sigma, is 20. And then you hover over this, and it turns black when you hover over it, and just press enter, and you should get the exact same answer, and you would just have to round. So that is literally with the TI-84, super easy. Now, z-scores is the way that College Board wants you to actually find the answer. So you get your z-score by doing, hold up, did I forget? I think I forgot. Hold on. Mu, it's either x minus mu divided by sigma. So really you're taking your point and you're subtracting your mu and you're dividing by your standard deviation. So really what they want you to do is they want you to convert your lower bound and wait, no, they want you to convert the point of interest into a z-score and then use a standard normal distribution to find your answer. With this one, we have been using the normal distribution with a TI-84 normal distribution as well. Even in Python, we've used the normal distribution. But there is this thing called the standard normal distribution, which is when the mean is 0 and the standard deviation is 1. With these, we have a mean of 150 and standard deviation of 20. So in order for us to use a standard normal distribution, we have to convert these values into z-scores, and this is a formula for it, right? So yeah, it's a lot. Okay, so basically we would just do 165 minus the mean, which is what again? 150, divided by the standard deviation, which is what? 20? So then that would be 0.75. So then that's my z-score. And I'll actually graph it in a few seconds just so we can get a visual of it. So maybe you can skip to that part and then come back to kind of understand what I'm doing here. So then that's really the equivalent. That's literally equivalent to 165, but in a normal, I mean, in a standard normal distribution, and this is just a normal distribution. So really now what I'm doing is I can do the same thing as I did in the TI-83, TI-84 in the same process, but the only thing I'm changing is or are the mean and the standard deviation, and I'm just putting, well, and also the lower. So literally these are what I'm changing here. So instead of, let me actually write it in a different color. So if I'm going to do it with the z-score method, it would end up having to be 0.75, 1e99, and then 0, and then 1. If I'm going to do it with the standard normal distribution. And then over here, it would have had to be 0.75, 1e99, and then 0, and then 1, because standard normal, again, is with mean of 0, standard deviation of 1, because it's standard, right? And then that's literally it. Yeah, that's it. And you would still get the same answer. Like, that's kind of the idea. So now just to kind of give a visual, I should probably plot the graph. So really what I'm looking at here, or what I want to look at, is the graph of the normal distribution with the given mean and standard deviation. So to do that, I think I already imported norm, right? So I don't need to do that. I should import numpy as np and import matplotlib to plot the graph, which is just a plotting library or graphing library. So then really we need our x values and our y values. So essentially our x values are basically our x values, so they're the student's heights, and then our y values is the basically the density or the probability of the student's heights, or I guess, um, yeah, it's the density. Um, yeah. So to get those, I'm just going to set up my x values and my y values. So again, my x values is going to come from np.linspace, and np.linspace takes in three um, parameters. Basically, it creates an array of values. So you can think of it as a list of your x values, and it takes in the starting point when you want to start, the ending point when you want to end, and then how many values you actually want. So for me, I would want it to start like three, so, okay, hold on. It'd be easier if I just draw it. So a normal standard deviation. What? A normal standard, I mean, a normal, what am I saying? A normal distribution usually has, it doesn't usually have, it literally has its mean at the center, and then it has three standard deviations from the mean to the left, and then three standard deviations from the mean to the right. That's kind of what it is. So I would want to represent that here in Python. So I'm just going to say mean, or I would just say 3 times the standard deviation, and then I would subtract that from the mean. So I want my starting point to be 3 times the standard deviation. So I want it to be here, is basically what I'm saying. I want it to start 1, 2, 3 times from the mean, right? Away from the mean to the left. So that's what the subtraction sign is. And then I want it to end after the mean 3 times the standard deviation. So in other words, I want it to end over here, because this is 1, 2, 3 times after the standard deviation, right? So then I would say, okay, I want basically let's say like 100 values. So I'll just go and put 100, like it literally doesn't matter. All right, those are my x values, done. Now the y values is actually what makes the actual curve is the density. So I would get norm.pdf instead of CDF, and PDF stands for probability density function. So you could ask yourself, what is the difference between PDF and CDF? Well, CDF is cumulative density function. So it takes, so if I ask you, okay, let's pretend this point was like 1. That doesn't make sense. Actually, it does make sense. 1, it doesn't really matter. And I'm asking, okay, what is the CDF of 1? So really what I'm asking you is what is the cumulative density up until 1? Because cumulative means all of it up until. If I ask you what is the probability density of 1, then I would only find the density of just 1, right? Not the cumulative, which is the purple, but just the probability density of just 1 is like the red. So that is the difference between PDF and CDF. So really, and it makes sense because we're trying to plot the y values are going to be the probability density of each single x value. So that kind of leads to the common sense that right now, really the only parameter that we really need is the x values, because that's what we're trying to find the probability density function, or the probability density of. And then we would also add the loc, which is the mean, and the scale, which is the standard deviation. And then I would just do plt.plot, which is a function that plots my values. So I'll do x values and y values, run that. All right, beautiful. This is our normal distribution graph. Now, just to kind of make it make sense, I can add a plt.title, and I'm going to put it in context. So in this case, this is middle school, what am I saying? Middle school students' heights. So I'm just going to say heights in centimeters, right? So that's what it represents. No, that's actually the x label. Whoops. And then plt.title is the normal distribution of middle school students' heights, right? And then this is making a space, and then I would say, um, with hold up. Where's the mu? Oh, here. Okay. With mean equals to, what's the mean again? 150. And standard deviation, which is sigma over here. Are you kidding me? I copied a space. All right, of 28. Run that. All right. So this is kind of the idea. I'm just gonna go ahead and right click, copy this image and just paste it in here. So really what I'm looking at right now, okay, let me pull this back. So what we just solved for is literally the following. So again, a set of middle school students' heights are normally distributed with the mean of 150 centimeters. Makes sense that 150 would be here in the middle because it's the mean. Yeah? Okay. And a standard deviation of 20 centimeters. Makes sense that 160 is what comes next because 50, well, actually, hold up. No, 150. 150. Okay, so the standard deviation is 20, meaning that really they deviate, each data point deviates 20, or in context, each height of a student deviates 20 centimeters from the average height, which is 150 centimeters. Okay, and then we're really looking for Uma's height, which is 165, so that's about kind of over here. So that's like 165. And what we're looking for, or what we did find actually, is the proportion that is higher than Uma's heights, or the heights that are higher than Uma's height. That is the area that we found, right? That is the area that we found with all that normal CDF stuff. Again, we started, so I hopefully it makes sense that normal CDF in the calculators, we start with the lower bound, upper bound, mu, and sigma for the normal distribution given the mean and standard deviation. The lower bound is 165 because we started at 165. And then we're trying to find the proportion to the right of that, higher than that, above that height, right? And that we know that it never ends. It's a continuous function that never ends. And because of that, this is infinity, and we had 1e99, right? So 165, 1e99, and then we know that the mu is 150 and the sigma is 20, and that is where everything came from. Now, what is the relationship between this and the z-score method? The only difference is I can literally copy this code and just make the standard deviation by just changing the mean to be 0 and the standard deviation to be 1. And then I'm just going to say the standard normal distribution, and that's going to be my, let's see, copy image, paste. That's going to be my standard normal distribution. So really what I did was, the only thing I did was just change it 165 to z-scores, which is kind of the conversion right over here. So 165 is literally in the same spot. Oops. If I graphed it right, if I can draw a straight line, it's literally in the same spot, which is 0.75. That was our z-score. So again, I hope you understand the relationship because, our z-score was 0.75, right? That is the equivalent to 165, except that it's in a standard normal distribution. So you can see, I hope you appreciate the fact that you can see that it's in the same spot, meaning it's equivalent. The only difference is just that, I don't know, College Board just wants you to, for some reason, do more work. I don't know, like they want you to understand kind of the concept of z-scores and how you can use them, but we're still finding the same thing, like literally the same thing. The only difference is numbers, and that's it. So in this case, it would be normal CDF. Lower bound again would be 0.75. Upper bound would be 1e99. That doesn't change because it's still infinity. it's still your interval, and then, it would just be 0 and 1 because, again, the standard normal distribution has a mean of 0 and a standard deviation of 1, which I probably should have fixed over here. 0 and 1. Let me fix that. Copy image. Whoa, did not mean to do that. How do I go back? Send back. All right, so that's the idea. And yeah, so that's kind of explaining pretty much everything. And yeah, and for Python, just to kind of explain how this works for Python, Python is just different, like spelled different. Um, Instead of using like lower bound, upper bound, it literally just takes CDF, and CDF only finds the proportion below a point, and then SF finds the proportion above a point. So you just have to know that. And if you want, you don't ever have to use SF. You could just do 1 minus CDF to get this stuff over here. So really, if we were to use norm.cdf, it would find the area to the left. So it would find this, oops, it would find this area here. And so in order to get the red area or the pink area, you would just have to do 1 minus this green area, and obviously you would get the rest of it, and that's kind of the idea. Or you could just do SF, and then you would just get this area here. But CDF basically gets the area to the left, and then SF gets the area to the right of a point, right? So that's kind of the idea for Python. And yeah, so that's it for today. I'm gonna go now. Pretty sure I covered everything, right? I don't even know. Anyway,